Hello, today we're continuing in our GCSE physics revision series looking at specific heat. Specific heat capacity tells you how much heat or energy can be stored, and that is different for different materials. Suppose you have 1 kilogram of water, H2O, 1 kilogram. If you want to change the temperature by just 1 degree Celsius, so for example if it's at 20 degrees and you want to raise the temperature by 1 degree to 21 degrees Celsius, you will have to put in approximately 4,200 joules of energy. Remember, heat is energy, so we measure it also in energy units, which is joules. On the other hand, if you have 1 kilogram, so it's the same mass as water, but this time it's 1 kilogram of copper, and you want to raise the temperature by just 1 degree centigrade, you only have to put in 385 joules of energy. If you have 1 kilogram of air, so same mass, just a different material, air, you'll need to put in 1012 joules to get a temperature rise of 1 degree. So clearly there's something about the chemical constituents of these different materials that means that the amount of heat you put in has to be greater for some of them than for others, just to get a single degree temperature rise. And this leads us to the thing called specific heat. Specific heat is the amount of energy you have to put in order to make 1 kilogram of a substance rise by 1 degree, which is exactly what we've been doing here. We had a 1 kilogram in each case. We wanted to change the temperature by 1 degree, and these are the amounts of energy we had to put in. So these are in fact the specific heat values for each of these substances. Let me just make it clear, we are not changing state at this stage. The state remains the same, all we're doing is changing the temperature. Specific heat, which usually has the symbol C, though sometimes you'll find it as S for specific heat, is measured in joules per kilogram per degree centigrade, or sometimes joules kilogram to the -1 degree centigrade to the -1. Because essentially you have to put in, for example in water, the specific heat would be 4,200 joules per kilogram per degree centigrade. So the total energy that you have to put into a substance in order to get a temperature rise of more than 1 degree will be the mass of that substance, how in kilograms, times the specific heat of that substance, which is common for each substance, times the temperature rise, which we call theta, which is the number of degrees centigrade that you want to increase the temperature. So here's a question. I've got 3 kilograms of water, and I've got that water at 20 degrees centigrade, which you could say is room temperature, and I want to heat it up to 100 degrees centigrade. I'm not changing state, so I'm not yet boiling it. It will be water at 100 degrees centigrade. How much energy do I need? Well, I use the formula above. Here we've got the formula. The energy is equal to mass, which is in kilograms. Well, I know it's 3 kilograms, times the specific heat. Well, I've told you the specific heat of water is 4,200. So that's 4,200 times the temperature difference. Well, the temperature difference is going from 20 to 100 is 80 degrees. So 3 times 4,200 times 80 is 1008,000 joules. So quite a lot of energy. You can rewrite that as 1008 kilojoules, where remember a kilojoule is 1,000 joules. So effectively we can drop 3 of the zeros here. That's a lot of energy, but then you are heating 3 kilograms of water over 80 degrees. Here's another question. I have a 0.5 kilogram block of aluminium. And I want to change the temperature from 30 degrees to 90 degrees centigrade. And in order to do that, I use 26,910 joules. And the question is, what is the specific heat of aluminium? Well, we go back to our formula, E equals mc theta, and now I've got to rearrange that formula for specific heat. So if E equals m times c times theta, then you've got to learn how to do this rearranging. C will equal E divided by m theta. If you like, what you're doing is you're simply dividing both sides by m theta. If you divide this side by m theta, you just get C. If you divide this side by m theta, you get E over m theta. So now we just put in the values. C is equal to E. Well, it took 26,910 joules to get the temperature change. The mass, we are told, is 0.5 kilograms, and the temperature change was 30 to 90, so that's 60 degrees. And if you work that out, you will get 897 joules per kilogram per degree centigrade. So the specific heat of aluminium is 897. So here's another question. An aluminium saucepan, and remember we just worked out what the specific heat of aluminium was. An aluminium saucepan weighs 200 grams, and we're cooling it from 120 degrees centigrade to room temperature. In doing so, it loses, because of course it's cooling down, so we don't have to heat it, it's going to lose heat. It loses 17,940 joules of energy. And of course we know that the specific heat is 897 joules per kilogram per degree centigrade, because we just worked that out. So the question is, what is room temperature? Well, we have to rearrange the formula E equals mc theta into a new formula which says that theta is E divided by mc. And that's going to be 17,940, because that's the amount of energy that we lost. Divide that by the mass. Well, the mass was 200 grams. That's got to be in kilograms, so that's 0.2 kilograms, times the specific heat, which we know, which is 897. And if you do that with the calculator, you should get that is equal to 100 degrees. Now 100 degrees is the temperature difference. We went from 120 to room temperature, and we're told that the temperature difference is 100, so we went down by 100. If you go down from 120 by 100, you find that room temperature is therefore equal to 20 degrees, because the temperature fell by 100 degrees. Remember that in all these examples we have not changed state. If it's a solid or a liquid or a gas, it always remains a solid, a liquid or a gas when we have these temperature changes. Storage heaters have high heat capacities. The idea with a storage heater is that you heat it up overnight when the costs of electricity are lower. Often electric companies will give you cheaper electricity at night when there is less demand, so that they've got a more supply, as it were, and can encourage the redistribution of the use of energy. And then the heater heats up overnight, and then during the day you switch the heat off, or you switch the electricity off, and the heater then radiates the heat out. And what you need is a storage capacitor that has a high heat capacity. Well, water, of course, as we saw, has a pretty high heat capacity, 4,200 joules per kilogram per degree centigrade. So that's one of the reasons why we use water in our central heating system. That is carrying a lot of heat to the radiators to be radiated out into the room. And water can be easily pumped round. A night storage heater might use cement blocks, which have a heat capacity of, or specific heat of cement is about 880 joules per kilogram per degree centigrade. And they hold the heat, and then in the day they release it. Now you might think, well, why would you use a cement block which has a specific heat of only 880, whereas if you had used water, that would have had a specific heat of almost 5 times as much. You'd have more heat in the water, and therefore more heat would come out during the day. But you've also got to think about practicalities here. How much water would you need? What would be the volume of the storage heater if you filled it with water as compared to cement? Cement is very, very much denser than water. So you get a lot of mass for a relatively small volume. So a night storage heater that's got cement in it will be smaller than a night storage heater that's got water in it. And you've obviously got to think about how big an object you want in your room, taking up room space. And it's a combination of the capacity and the volume of the device which determines what you use for your heat capacity medium. So what we can say is that for any substance, it will have a specific heat capacity, C. The higher the value of C, the more energy you have to put in to heat it up, in other words, to raise the temperature, the more energy it will then contain, and therefore the more energy it can give off into the room. So far I've stressed that we have not been changing the state of the material. Now we're going to think about changes of state. So now we're going to think about what happens when you go from solid to liquid to gas. And these two have specific heats associated with them. When you go from solid to liquid, the specific heat is called the specific heat of fusion, or sometimes of melting. When you go from liquid to gas, that is called the specific heat of vaporization, or sometimes boiling. So there are two types of specific heat, and they're both called specific heat. One of them simply gets the temperature to rise, but keeps the state the same. The other one changes the state from solid to liquid or liquid to gas, but keeps the temperature constant. We're now doing this one. Now, if the heat that is going into this is not changing the temperature, what is it doing? Well, the answer is it's breaking the bonds. In the case of solids, they have very strong bonds holding the molecules together, and what that heat will do is to break those bonds and make them much weaker, and that turns the material into liquid. If you're going from liquid to gas, you've got weak bonds, you add heat, you add energy. That energy breaks those bonds still further till the molecules are hardly affected at all, and they are, to all intents and purposes, free. So the energy has not gone into raising the temperature, but breaking the bonds. So to be clear, if you want to go from ice at 0 degrees centigrade to water at 0 degrees centigrade, no change in temperature, you need to put in heat, energy. If you want to go from water at 100 degrees centigrade to vapor, water vapor at 100 degrees centigrade, you need to put in energy in the form of heat. You don't change the temperature, you do change the state. And how much energy do you need to put in? Well, it's rather like the formula we had before. It's the mass in kilograms multiplied by the specific heat, but now you need a specific heat of fusion or vaporization, depending on whether you're melting or boiling. But you don't need a temperature difference term, which we had before, because there is no change in temperature. So that is actually the formula. The energy you need is the mass multiplied by the specific heat of fusion or melting or vaporization, boiling. Now you may recall that the specific heat of water was 4,200 joules per kilogram per degree centigrade. The specific heat of water for fusion, that is if you're going from solid to liquid, is 334,000 joules per kilogram. Obviously it's not per degree centigrade because you're not changing. That is almost 8 times bigger than this value here. And the specific heat for water of vaporization, or as it were boiling, is a staggering 2,260,000 joules per kilogram. And that is almost, or is about, 540 times 4,200. So a massive amount of heat has to go into water at 100 degrees simply to convert it into vapor at 100 degrees. And quite a lot of heat has to go into ice at 0 degrees just to convert it into water at 0 degrees. Breaking the bonds takes a lot more energy than simply raising the temperature of a given state by a few degrees centigrade. Indeed, as I shall show in a moment, you need more energy to take water at 100 degrees centigrade and turn it into water vapour at 100 degrees centigrade than you would use if you took ice at 0 degrees centigrade, converted it into water at 0 degrees centigrade and heated it all the way up to 100 degrees centigrade. Let's do that as an exam question. First we'll melt the ice and take it up to 100 degrees centigrade. So we'll assume that we've got 1 kilogram of ice, which will become essentially 1 kilogram of water. So the first thing we've got to do is to melt the ice. And the energy that we require is the mass of the ice times the specific heat of fusion, or the specific heat of melting. And that's going to equal, well, we said we were going to use 1 kilogram, so it's 1 times the specific heat of fusion, and if you can recall, that was 334,000. So that's going to equal 334,000 joules. Now we need to raise the temperature from 0 to 100 degrees. So the energy now is going to be the mass times the specific heat of water, this is not fusion or boiling, times the temperature change. Well, that's going to be 1 because it's a mass of 1. The specific heat for temperature change, remember, was just a mere 4,200, and the temperature change is 100, sorry, that should be a times 100 because we're changing it by 100 degrees, and that's going to be 42,000 joules. So the total energy for melting and raising the temperature is 334,000 plus 42,000, which is 376,000 joules. So just to remind you, for 376,000 joules, you can take a 1 kilogram block of ice, you can melt it, and then you can raise the temperature from 0 to 100 degrees centigrade. Now let's suppose you want to boil it. So this is the boiling energy, and again that's going to be the mass times the specific heat of boiling or vaporization, and that's going to be 1 times, and do you remember the staggering figure? It was 2,260,000. So that is going to be 2,260,000 joules. So you needed 2,260,000 joules just to boil water when it's already at 100 degrees. But you only need 376,000 joules to melt a kilogram of ice and raise its temperature by 100 degrees. You need huge amounts of energy to vaporize water. So you might want to think about this when you next boil your kettle. You put the water in the kettle, of course it isn't ice. You're using relatively little energy to raise the water from room temperature to 100 degrees. But if you let the kettle continue to boil, then you're using a huge amount of energy to change the water into vapour, which you usually don't want because you're boiling the kettle because you want hot water, not because you want vapour. So it's a good idea to switch off the kettle as soon as it boils, otherwise you're wasting vast amounts of energy in converting water into vapour. So let's now draw a diagram to illustrate what happens as you add heat to a system. So I've got the temperature going up in this direction, and I've got heat being added to the system in this direction. And I'm going to start with a solid. It doesn't have to be ice, this applies to anything. So I heat my solid, which means I'm putting heat in, and as I put heat in, the temperature increases. So this is a solid being heated and rising in temperature until it gets to its melting point. And this is the melting point on the temperature scale. At that point, any further heat will not raise the temperature, it will change the state. So there will be a certain degree of heat that you will need that keeps the temperature at the same level, but changes from solid to liquid. And once that's happened, you add more heat. Now you will raise the temperature of the liquid until you get to its boiling point. When you get to its boiling point, any further heat will now keep the temperature the same but change the state to gas. And when it's all changed to gas, if you keep heating, the gas itself will get hotter. So the solid gets hotter as you heat it till you get to the melting point, at which point the temperature doesn't change, but the state changes from solid to liquid. When it's all changed to liquid, now the temperature rises as you continue to heat it until you get to the boiling point. At that point, the temperature no longer rises, but the state changes until all the water has changed into gas. And then if you continue to heat it, the gas itself will increase in temperature. And of course it works in exactly the same way the other way round. If instead of adding heat, we take heat out, that is to say we cool, so we're cooling now in this direction, the temperature is still in this direction, we start with a gas, we cool it, the gas just gets cooler and cooler until we get to the boiling point, at which point the gas will now condense, and as you take heat out, the temperature stays the same, but the gas changes into a liquid. When it's all changed into a liquid, as you continue to cool, the liquid will fall in temperature. So this was gas, this is liquid, until you get to the melting point. When you get to the melting point, or in this case, of course, in the direction we're going, the freezing point, now as you cool it, as you take energy out, you don't lose temperature, you change the state from liquid to solid. And when it's all a solid, if you continue to cool it, then the solid will go down in temperature. So just to remind you, when you want to change state or increase temperature, when you want to change state from solid to liquid or liquid to gas, or increase temperature, you have to add heat. If you want to reduce the temperature or change the state such that the gas condenses to a liquid or the liquid freezes to a solid, you have to take heat away, which means you're cooling. So here's an exam question. 2 kilograms of water are frozen to ice. How much heat is taken out? And we'll assume that we're at 0 degrees centigrade. So there's no change in temperature, there's just taking heat out of the system. Well, energy, remember, was the mass times the specific heat of fusion, or the specific heat of melting. The mass in this case is 2 kilograms, so that's 2 times the specific heat of fusion, you may recall, was 334,000, so that's going to be 668,000 joules, or if you like, 668 kilojoules. And that is the energy you take out of the system because you're freezing it. You're taking energy away, it's cooling. So that's the energy you get out, or that's the energy you essentially have to take away in order to convert the water into ice. Energy is sometimes measured, though not in the SI units, in what's called calories. And this is what you'll often see listed for food. And you will often hear people talking about the number of calories they take in. Calories are a source of energy. 1 calorie is required to take 1 gram of water through 1 degree centigrade. That's how it was originally defined. So it's not in SI units. So 1 calorie takes 1 gram of water through 1 degree centigrade. So 1 kilocalorie of heat will take 1 kilogram of water through 1 degree centigrade. But of course that is also the specific heat of water, 1 kilogram for 1 centigrade. So that is 4,200 joules. So essentially 1 kilocalorie is 4,200 joules. When people say that a food has 100 calories, what they actually mean is that that is 100 kilocalories. 100,000 calories in the strict definition of what a calorie is. So effectively, whenever you see something that is listed as being 100 calories of intake, what that actually means is 100 kilocalories of intake. And if you multiply a kilocalorie is equal to 4,200 joules. So in other words, 1,000 calories is equal to 4,200 joules. Usually food is listed in both. So for example, if it says 100 calories, it means 100 kilocalories, and that is equal to 420 kilojoules. So to summarise, there were only 2 equations that we needed in the whole of this video. If you are raising the temperature but not changing state, then the formula you need is that the energy you need to put in is the mass in kilograms times the ordinary specific heat times the change in temperature. If, on the other hand, you're changing state, then the energy you need to put in is again the mass multiplied by the specific heat, either of fusion, which is melting, or vaporization, which is boiling. And what you'll need to be able to learn how to do is, as I've said before, is to rearrange these formulae, because you might be given, say, the energy, the mass and the specific heat and asked to find the temperature. You might be given the specific heat and the energy and asked to find the mass. So you need to be able to manipulate these formulae to be able to work out whatever the exam question is asking.